Okay, I'm going to talk to you about a couple key ideas here. I'm going to talk to you about something called collision theory, and then I'm going to talk to you about something called activation energy. So, what I'd like you to do is first imagine that we've got we've got a diatomic molecule here that consists of red and blue. And let's pretend this is like, I don't know, NaCl. And we have another molecule that's also diatomic over here. So we have these two molecules, both are bound together. And what we remember from earlier in this semester is that these have a bond between them. This has a chemical bond to red, and green has a chemical bond to purple. So if I want to see a chemical reaction happen, let's say my products look like this. So if I want a chemical reaction to happen, then what needs to happen is the bonds on the left need to break, and then these new bonds on the right need to form. So I need bonds here to break so that these bonds can form. And so in order for that to happen, in order for any reaction to happen, we need the atoms to bump into each other, because the way they're sitting right now, if I have this red molecule and it is going towards, let's imagine we're in like an actual container. So let's take ourselves out of our reaction for a second and just pretend we have our starting reactants. We're in an actual container. Let's pretend we've got a solution going on here, full of maybe this reaction's happening in water. So let's put it in a cup. That's an ugly cup, but you guys get the idea. Here's some water. So my reaction's actually happening, and I have these two molecules. They're floating around in water. And if I think about the actual reality of these molecules, then if they bump into each other like this, there's not going to be a reaction that happens, because as you can see in my products over here, red and green aren't trying to bond together. My red and purple are what end up bonding together, and my green and blue bond together. So not only do they have to bump into each other, but they have to bump into each other in just the right way. So if they bump into each other like this, nothing's going to happen, because red doesn't want to bond with green. But if they bump into each other, and I'll say if they bump into each other like this, again, nothing will happen because purple and blue aren't going to bond. But if they happen to bump into each other just right, like this or like this, then we reach what's called a transition state, which is what I have going on here. So my transition state looks like this, where I have all the pieces oriented correctly. They've bumped into each other. And now these bonds here can break, while these new bonds form right here and right here. And so then these can break apart, and I'll have my products. Now I've got my red-purple product and my blue-green product. So a couple of things happened there. I know my diagram got pretty messy, but a couple of important things happened there. So number one, my molecules had to bump into each other. They have to collide with one another. And then we said not only do they have to collide, but they also have to collide in the correct orientation. If they collide in the wrong direction, if they collide where the atoms that aren't trying to make a new bond bump together, then nothing is going to happen. So the molecules have to collide in the correct orientation. And then there's actually one more factor here. So if I go back to my transition state, but when I've got everything kind of hanging out together, but not quite a new bond, not quite breaking my old bonds, when it was kind of like this, let's say that when I had my starting materials, they bumped into each other, but they did so really slowly, like this. Instead of bumping into each other in the right orientation really fast. They bump into each other, it's in the right orientation, but it's really slow. Well, then we're actually not even going to have enough energy to break these starting bonds that we had. So those bonds aren't even going to break unless we hit pretty hard. So the third factor I have here is that my molecules must actually collide with enough energy, which in this case is going to be kinetic energy, so they have to hit each other fast enough. All right, so those are the three factors that have to happen in order for a reaction to occur. All right, so then what we can actually kind of think of our reaction kind of mechanism as is this is our in-between state. These are our products, and what we started out with were my blue, red, and my green, purple. So we can kind of think of our whole reaction as actually we have our reactants, and then we have our products, and then we have this transition state, which is this place we get to in between when we haven't quite turned into our products, but our molecules have collided and they've done so in the correct orientation. And the amount of energy that they have to get to this state, that's going to be called my activation energy. So the amount of energy, amount of energy required to get here equals, and I'm going to write it like this, a big E with a little subscript A. That's our abbreviation for activation energy, E with a little a. So inside my container, I have my reactants. They bump into each other in just the right way. And then the bond here and the bond here start to break while these new bonds start to form. And that's really what's actually happening between my atoms in order for my bonds to break over here and these new bonds to form. So the other thing that this energy is doing is breaking those bonds in my reactants. So I'm going to put just a definition down here at the bottom, and that'll wrap this first video up for us. So activation energy is the amount, let me shrink this down, of energy required for a reaction to occur. All right, so that's our definition for activation energy here, and we write it as a big E with a little subscript A.